A process flow diagram is not just an early engineering drawing. It is the first disciplined visual definition of how a process is expected to work. When you develop a PFD correctly, you create a common technical language for process engineers, instrument engineers, mechanical engineers, electrical engineers, piping designers, materials specialists, estimators, project managers, customers, and eventually operators. When you develop it poorly, every downstream discipline is forced to interpret incomplete intent. That interpretation becomes assumptions. Assumptions become design changes. Design changes become rework, delay, and cost. A strong PFD answers four fundamental questions. What enters the process? What happens to it? How is the process controlled? What leaves the process? It presents the major equipment, connecting flow paths, operating conditions, material transformations, and primary control functions required to understand the process. It should be detailed enough to support engineering decisions, but not so overloaded that it becomes an immature P&ID. That distinction matters. A PFD defines the process. A P&ID defines how the process will be physically implemented, controlled, isolated, protected, operated, and maintained. The PFD is normally prepared early in the project because every major design discipline needs a stable process basis before detailed engineering can proceed efficiently. It depicts the sequence of operations that physically, chemically, or biologically converts feedstocks into products, byproducts, and waste streams. The PFD is usually supported by a heat and material balance. This balance may appear as a table within the drawing or as a separate controlled document. Together, the PFD and heat and material balance establish the process conditions that drive equipment sizing, utility demand, material selection, control philosophy, piping design, and cost estimation. You should never treat the PFD as a document owned only by the process department. The customer uses it to review and approve the process concept before detailed engineering advances. It communicates project scope across customer departments and later becomes a useful overview for operator training and operations support. The project manager uses it during early design reviews, value-improving studies, and preliminary hazard reviews. At this stage, major process weaknesses are still relatively inexpensive to correct. The instrument engineer uses it to align with the process engineer on control philosophy. The PFD should reveal the basic control schemes before hundreds of instrument tags, interlocks, and signal connections appear on the P&IDs. The mechanical engineer uses it to determine the number, type, and approximate size of major equipment. Stream duties and enthalpy differences influence exchanger selection, rotating equipment requirements, and potential supplier identification. The electrical engineer studies major driven equipment, preliminary motor loads, and the likely need for variable frequency drives. The piping and layout teams use process temperatures, pressures, and equipment relationships to begin plot plan development and preliminary piping specification selection. The materials engineer examines stream composition, temperature, pressure, phase, and contaminants to identify suitable metallurgy and corrosion-resistant materials. The estimator uses the PFD as a basis for the preliminary project cost estimate. This is why a PFD must be technically coherent. One diagram influences multiple decisions simultaneously. A typical PFD should identify all significant feed streams, products, byproducts, and waste streams. It should show major process piping and all major equipment items using clear symbols, names, and equipment numbers. Where equipment internals affect process understanding, show them. Trays, packing, baffles, demisters, filter elements, vortex breakers, and similar internals may be represented when they explain equipment function or influence downstream design. Show control valves and major manual valves only when they are essential to understanding normal process operation. A heater pass throttling valve or a block valve that redirects flow between operating systems may be important. A routine isolation valve normally is not. Show connections to other process and utility systems clearly. Include chemical injection systems required during normal operation. Show major bypasses and recirculation streams used for routine operating purposes. Temporary startup or shutdown aids should not dominate the diagram unless they are critical to understanding the process. Operational information should be linked to numbered streams and the heat and material balance. Depending on the project, this may include temperature, pressure, mass flow, volumetric flow, density, phase, composition, molecular weight, viscosity, or enthalpy. Stream names and numbering must be logical and consistent. Names are commonly placed at drawing continuations or at the boundaries where feeds, products, and utilities enter or leave the process unit. The PFD should also show simplified control bubbles identifying the controlled variables such as pressure control, temperature control, flow control, or level control. Do not stop at simple feedback loops when the process requires more. Show relevant cascade arrangements, master-slave functions, ratio control, calculated control functions, and other basic control relationships necessary to explain how the process will remain stable. Flow elements and significant inline devices should be shown where they influence the process concept. Add notes where the P&ID team must preserve a particular piping arrangement, hydraulic relationship, control requirement, or equipment connection. Notes should resolve ambiguity, not create it. Now consider what should normally remain outside the PFD. Do not clutter it with piping line numbers, pipe classes, or routine pipe sizes. Do not show every sensor, transmitter, indicator, recorder, switch, or final control element. Do not include every minor bypass, isolation valve, shutoff valve, maintenance vent, drain, flange, or spectacle blind. Relief valves and other safety devices are normally developed at the P&ID stage unless their presence is essential to explaining the process concept. Pump minimum flow recirculation lines, nitrogen purges, steam out connections, and maintenance utilities are usually omitted unless they form part of the fundamental process arrangement. Pressure and temperature indicators are generally not required. Insulation, cladding, tracing, and other installed features normally belong elsewhere, although heat tracing may be identified when it is essential to maintaining process operability. The test is simple. Does this information explain or does it merely describe detailed implementation? If it does not improve process understanding, it probably does not belong on the PFD. Consistency begins with symbols and numbering. Use the approved equipment symbols and customer conventions applicable to the project. The symbol must represent the correct equipment type and orientation. When no standard symbol exists, draw the equipment so that its physical characteristics and function are understandable. Maintain reasonable proportions without turning the PFD into a layout drawing. Number every major equipment item. Show the equipment number next to the symbol and apply the approved equipment numbering philosophy consistently. Standby and parallel equipment can often be represented by equipment numbering rather than duplicated full detail symbols. The diagram should communicate configuration without unnecessary graphic repetition. Avoid placing detailed equipment design information on the PFD unless the customer specifically requires it. Equipment capacities, dimensions, design pressures, metallurgy, and nozzle data are normally controlled through equipment data sheets and specifications. Equipment titles should be concise, descriptive, and based on agreed project terminology. Place equipment titles and numbers along the top of the drawing, aligned vertically with the relevant equipment wherever practical. Rotating equipment may be shown along the bottom when this improves readability. The entire drawing should tell a visual story. Process flow should generally progress from left to right. Recycle lines may naturally return from right to left. Streams arriving from an earlier PFD normally enter from the left. Streams continuing to a later PFD normally leave from the right. This is a convention, not a rigid rule. Readability always takes priority. Avoid bringing major streams through the top or bottom boundaries unless there is a compelling reason. When the process cannot be shown clearly on one sheet, divide it into logical sections. Do not divide drawings merely to satisfy arbitrary sheet density. Each sheet should represent a coherent process function. Every cross-sheet continuation must be unmistakable. Use a boxed continuation arrow showing the source or destination drawing number. Add a clear text description and include the related equipment number where relevant. Continuation should never force the reader to search through several drawings to determine where a stream came from or where it goes. When different process options are under evaluation, show them on separate PFDs. Overlaying competing configurations on one drawing creates confusion and weakens review quality. Stream numbering must align with the heat and material balance. Assign numbers to all major process streams in a logical sequence. Number startup, shutdown, or recycle streams only when they are important to the process and have defined data in at least one operating case. Utility streams may be numbered when heat and material balance information is available. Numbering between the shells of a multi-shell exchanger is normally unnecessary unless material is added, removed, or changed between shells. Brownfield modifications require particular care. New stream numbers may be needed when existing flows are split, combined, or redirected. A seemingly small modification can change the mass balance across multiple units. Exchanger representation must be technically clear. Identify shell side and tube side streams wherever possible. When the allocation is still undecided, use a neutral exchanger symbol rather than inventing a design decision. Represent a multi-shell exchanger with one main symbol and suitable shell designations. Use equipment suffixes consistently to distinguish multiple shells from identical exchangers operating in parallel. Line hierarchy is equally important. Show major process lines in a bold line weight. Use lighter lines for secondary connections. Mark stream direction clearly between equipment items. Include minor lines only when they are essential to understanding normal operation. Where a line is installed but normally has no flow, identify it clearly as normally no flow. This prevents reviewers from interpreting it as an active process path. Packaged systems demand deliberate treatment. A licensed process package or third-party package may be enclosed within a dashed boundary to identify the package limit. However, the package must not become a mysterious box with unexplained inputs and outputs. Show enough internal equipment and functional information to explain what the package does, what conditions it requires, how it interacts with the surrounding process, and what responsibilities exist at the interface. Package boundaries are commercial and engineering interfaces. If they are vague on the PFD, they will become disputes during detailed design, procurement, construction, or commissioning. A good PFD is also a process optimization tool. Challenge the need for every major equipment item and flow path. Ask why the equipment exists. Ask whether two functions can be combined. Ask whether a recycle consumes unnecessary energy. Ask whether the process can operate under startup, normal, turn down, upset, and shutdown conditions. Ask whether the control scheme can actually maintain the required pressure, temperature, level, flow, composition, and equipment protection limits. Do not show an attractive control loop that cannot work dynamically. A control valve requires adequate pressure drop. A level controller requires sufficient surge volume and response time. A temperature controller requires a manipulated variable with real influence over the process. A pressure controller must have somewhere meaningful to send or remove material. A ratio controller requires measurable and controllable flows. The PFD review is the right time to challenge these fundamentals. Instrumentation should remain simplified. Show the control valves and elementary instrumentation necessary to communicate the process control concept, but do not assign detailed instrument or valve tags prematurely. Detailed numbering belongs in the P&ID and instrument database once the control philosophy has matured. Special process requirements should be captured through clear notes. This may include operating constraints, required elevations, gravity flow conditions, minimum static head, vapor disengagement requirements, mixing limitations, exchanger arrangement, phase separation requirements, or package interface conditions. Where licensed technology is involved, include the required confidentiality statements and restrictions. The heat and material balance must be treated as an integrated part of the PFD, not as a disconnected calculation file. Show data for every numbered stream. Verify that the properties and units satisfy customer requirements. Use consistent pressure references, temperature units, flow bases, and composition conventions. Clearly distinguish operating pressure from design pressure. Clarify whether gas flow is actual or standard. Clarify whether liquid flow is mass-based or volume-based. Avoid mixing gauge and absolute pressure. Do not allow simulation output to be exported into a table without engineering review. A process simulator calculates what you ask it to calculate. It does not verify that your design basis is correct. Separate balances should be prepared for different design cases and operating modes when required. These may include normal operation, maximum throughput, minimum turndown, different feed compositions, summer and winter conditions, startup circulation, or alternative product modes. One operating case rarely defines every equipment and control requirement. Review and approval determine whether the PFD becomes a dependable design basis or merely an evolving sketch. The drawing should undergo disciplined internal checking, interdisciplinary review, and customer review. Process engineers must verify mass and energy continuity, operating conditions, equipment functions, and control logic. Mechanical engineers must confirm that the represented equipment is practical. Instrument engineers must challenge controllability and manipulated variable selection. Piping and layout engineers must identify impossible routing, elevation, or hydraulic assumptions. Electrical engineers must confirm major drive implications. Materials engineers must challenge corrosion and metallurgy risks. Operations representatives must test whether the process can be started, controlled, isolated, and shut down sensibly. The objective is not to collect signatures. The objective is to expose contradictions before they reach detailed engineering. Ideally, the PFD should be issued for design before P&ID development begins. Projects sometimes start P&IDs early to protect the schedule. This may appear to save time, but an unstable PFD transfers unresolved decisions into a much more detailed document. A single PFD change can alter equipment connections, line lists, valve counts, control loops, relief cases, instrument indexes, cause and effect logic, layouts, cable schedules, and cost estimates. Starting P&IDs before the PFD is sufficiently mature usually creates more work, not less. Before issue for design, complete the planned customer reviews, interdisciplinary reviews, value improvement studies, and preliminary hazard reviews that depend on the PFD. After issue for design, changes must be controlled formally. Every major change should state what is changing, why it is changing, which documents are affected, and who has approved the change. The PFD may later be reissued to reflect P&ID development, hazard review actions, supplier data, machinery design, combustion design, or final as-built configuration, but reissue only when it adds controlled value. Repeated unnecessary reissuing of PFDs and heat and material balances creates competing versions, review fatigue, uncertainty, and avoidable rework. The final discipline is document clarity. A reviewer should be able to trace the main process path quickly. The equipment sequence should be obvious. Stream numbers should connect directly to the heat and material balance. Control functions should explain how the process is stabilized. Package boundaries should be visible. Continuations should be unambiguous. Notes should clarify exceptions. The drawing should be technically dense but visually calm. That is the real standard. A good PFD does not try to show everything. It shows exactly what every discipline needs to understand the process, challenge the design, and proceed with confidence. When you build the PFD with discipline, you reduce downstream assumptions. When you reduce assumptions, you reduce changes. When you reduce changes, you protect engineering hours, procurement decisions, construction productivity, commissioning safety, and plant operability. So before approving your next PFD, ask one final question. Does this drawing merely show equipment connected by lines? Or does it communicate a process that can genuinely be designed, controlled, operated, and maintained? That difference is where engineering quality begins. File site turn file 0,